Hello, this is a demo of calibrating a thermocouple calibrator for ELE 8931 instrumentation. It's February 2014 and Michelle Hanbury is the presenter. So to begin with, I'm going to show you this thermocouple transmitter. We've got it hooked up so that the negative and positive of the power supply go through this current loop. It's going through a 250 ohm resistor so that when it is calibrated we'll get 1 to 5 volts. On the other end I've got the positive and negative of the sensor connected to a thermocouple calibrator. The idea behind this thermocouple calibrator is that it will output the millivolts, microvolts as if a real thermocouple were connected to this device. Now, since our transmitter has a range of 0 to 300, it's a K3, I have to make sure the calibrator is set for type K and degrees Fahrenheit. And you do that by pressing the shift button. So for example, if I want to change it to Celsius, I do shift, Celsius. I'm going to change the type, shift, hit the button until I've got the right type. I'm going to go back to K, shift to get out of that mode, and then back into Fahrenheit. Okay, so we've got everything that we need here. Now to begin with, I want to show you that the calibrator is at 0 degrees Fahrenheit and we're reading 0.7 volts, 0.7 volts. Now to find out what current that represents, divide it by 250 ohms, and that's going to give me 0.7 divided by 250, 2.8 milliamps. Okay, so my current for my minimum is too low, so we're going to have to adjust the span clockwise. Now if I go to the maximum temperature, hit enter, my voltage is 5.53, and if we divide that by 250, that gives us 22 milliamps. So our span is too wide because it should be 16 and we're over that. So span is too wide and the 0 is too low. So we're going to adjust the 0 clockwise and the span counterclockwise to fix it. Now don't forget, it's going to take more than one try to get this right. So let's just give this a try. So back to 0 because that's what you have to adjust first. And at 0 I'm getting 0.7, but I should get 1 because 4 milliamps going through a 250 ohm resistor should give me 1 volt. So I'm going to adjust the 0 and we'll watch the meter. And we said we have to turn it clockwise. I'm going clockwise and I just want to get very close first because I know I'm going to have to go back. So there's no sense being perfect. And then we go to 300, enter, and we're way too high there. And so we're going to go counterclockwise because we were too wide. Watching the meter. And it's a 10-turn pot, so you have to turn it quite a bit. And we just have to get close until we're close on both sides. So back to 0. So too low. And every time we make an adjustment, it affects the other less and less. So we want to get closer each time we do this. So 1, 300. Didn't change by much, but we still have to make a change. We're getting close. Okay, that's 5, 0. That didn't change as much this time, so we're going to try to get it closer. Back to 300. Ooh, very close. Sometimes I find it hard to get the screwdriver right in the correct position. So 5 volts at 300. And back to 0. Ooh, I don't think I'll get much closer than that. So realize this is 5 off out of 995 millivolts. So better than 1%. That's good enough. So 300 again, just to double check it. 5 volts. 0. Now, what should it be halfway? So if we have 0 to 300, halfway is 150 degrees, and that should give us 3 volts. Let's just try that out. So 150 degrees, Pretty close. Okay, realize that we're 2 off out of 300, so that's still better than 1%. Let's go to 75. That should give us 2 volts. Still pretty good. We're 4 off out of 200, so maybe 2 off out of 100, so 2%. So now we'll go to 225, and that gives us 4 volts. So we're pretty close on all of those settings. Back to 0 just to recheck it, and that's good. Now the other thing I wanted to show you is what happens if the loop breaks open. Well, what's supposed to happen is you're supposed to get 3 milliamps. So I'll break open the loop here. Sorry, to get 0 milliamps, but 0 milliamps flowing through that 250 ohm resistor should give you 0 volts. Okay, so that proves that the open loop gives you 0 milliamps. And what happens if you have an open sensor? Well, we're going to simulate that by breaking this connection. We just did that. Get the wire out of the way, and I'm on a range where I have to increase that range. So it went to 7.85 volts. Well, that's 7.85 across a 250 ohm resistor. So 7.85 volts divided by 250 equals 31 milliamps. So as I said in the theory class, it's going to go way over the expected current. So let's just review. This is a 249 ohm resistor, but that's close enough to call it 250. And its color code is red for 2, yellow for 4, and white for 9, 249. And the brown stripe on this side indicates it's a 1% resistor. And I think that's about it for the demo. No, I wanted to show you a couple of other things. Now that it's calibrated, I'm going to reconnect the loop. Okay, and we're back to our 1 volt at 0, but I'm going to go to the maximum current, which is 5 volts across the 250 ohm resistor. And what I'm going to do is take my meter off of that 250 ohm resistor and measure across the power supply. Sorry, the power supply connection on the transmitter. As my power supply is set to 20 volts, and I'm just going to measure across here. Hopefully you'll see it on the meter. And we're getting 15 volts. Okay, that makes sense because we've got 5 volts across the resistor, 20 on the power supply, so the remaining voltage should be across the transmitter power supply terminals. Now I'm going to reconnect this, show you one last important thing. Okay, so my output is at 5 volts right now at 300 degrees. And I'm going to, this part you're not going to see, but you'll have to trust what I'm doing here. And I can actually do this by, I could do it by having 2 meters, but I only have 1. So I'm increasing the power supply to 25 volts. Okay, what happened to my voltage across the resistor? It didn't change, and that's approximately 25. But what's going to happen is that across the transmitter, kind of hard to do this without blocking the meter, but we have about 20 volts across the transmitter now, and that's because with the voltage drop is still 5 volts across the resistor. Now I'm going to bring the power supply down to 15 approximately. It's just hard to get it exact on my meter. And now I'll measure this again. And we're getting about 10 volts, okay, 15 minus the 5. But now when we reconnect this, we're still getting 5 volts, okay? So I changed the power supply all the way from 15 to 25 volts when it was normally at 20. So I had a large change in the power supply, but it didn't affect the voltage to the resistor. And that's because it changed the voltage across the minus and positive power supply leads of the transmitter. So it's the transmitter compensating for that difference. So you can see that you can go a long ways. But here's what happens if I bring the power supply too low. Okay, we're at 15, so that leaves 10 across the transmitter. This is at 10, and still pretty good. Okay, I've still got 5 volts there. But here I've gone way too low. I have 6 volts and I'm not getting a correct reading here. So I don't have the correct bias voltage for the transmitter. Back up to 20, which was my original, and I get the correct reading. Okay, and this test is normally best done with the highest output, which is giving us the greatest current of 20 milliamps with 5 volts across the resistor. Thanks for viewing the demo. Bye for now. Good luck with doing this on your own.